So we're going to look at a communication fiber laser. This is running 1550 nanometers. It's a eye safer wavelength. It is not eye safe. I think we've mentioned this before about 1550 being in some literature that it's eye safe. There's no such thing as an eye safe laser unless the output is below the MPE. That's it. And these lasers are fully capable of being well above the MPE. It's just that they're eye safer because the entire volume of your eye is absorbing energy, which means it can take more energy before you run the risk of a hazard. Okay, so I just want to stress that there's no such thing as an eye safe laser. There are outputs or wavelengths that are eye safer, but yeah, no such thing as an eye safe laser unless the output is below the MPE. Okay, so we have 1550 continuous wave, 200 milliwatts. We're using the ANSI default exposure duration for this wavelength. We have a beam diameter at the waist of 2 millimeters, a beam divergence of 1 milliradian, 1 over e squared, circular Gaussian. And so what we're saying here is that this fiber laser has been collimated to 2 millimeters. Now, at where our observer is at a half a meter, we have an OD requirement of 1.316. Worst case is 1.318. So that tells us, yeah, right over here, a little bit of difference in how much of the power is being transmitted through the limiting aperture versus all the power being transmitted through it. It's like 99.7%, but we see it in this third decimal place right here. So when you see little things like that, look around and see if you can pick up what's where that's coming from. Okay, because bear in mind that this is all about number manipulation, and so sometimes it's rounding that's going on, stuff like that. But a lot of times we can just look around, and particularly at this transmission through the limiting aperture, figure out where little variations in these numbers come from. We have an NOHD of a little over 22 meters and an NSHD of, the same. What does that tell us? That tells us that the MPEs are the same for the ocular MPE and the skin MPE are the same for this particular wavelength. And then we take a look down here, this small beam, we can see that the irradiance of our laser is about 20 times higher than the MPE. So is this a skin hazard? Well, as an LSO, I would say yes. I would tell the user that, yeah, if you put your hand in this beam, it's not going to be too bad, okay? Yeah, we have an average power irradiance in the limiting aperture of 2 watts per square centimeter. We have an MPE of 0.1 milliwatts per square centimeter. But at 200 milliwatts, you might feel it, but it's certainly not going to be something that is going to be much of an issue. So in this case, I would just caution people, be careful. And if you stick your hand or your arm in it, you may feel it, but nothing much is going to happen there. You can take a look at the diffuse reflection stuff. What we're really going to be interested in is the fact that we want to look at what this fiber is. Now, it's a single mode fiber, so we're going to come down here and select single mode, and we have mode fill diameter. Now, if you say, well, the mode fill diameter is 9 microns, and you're not up to the difference between what 9 microns is and what is that in nanometers, just come up here and switch this to microns. Come down here, input your 9 microns. Then you can come back up here if you're one of these people that says, but I like to work in nanometers, I want to see nanometer up there, fine. Put it back up there and it'll switch to 9,000 nanometers here. Okay, what's our observer range? 1/4 meter. Okay, that's pretty standard for what we put for putting a fiber up close to your eye. You wouldn't be any closer than that. And so the OD at observer range is 0. That's because we have an NOHD of just 10 centimeters. Okay. So something I want to point out here is that if you take a look at the ANSI standard in Appendix B and you look up mode field diameter, which is omega naught, it'll be the last thing in Appendix B in the terms or definitions. Okay, it'll tell you that the mode fill diameter, we look at that as sort of the beam waste at the 1 over e squared points, which means I should be able to duplicate this up in the intrabeam section. Okay, how would I do that? Well, let's see. First off, I'm going to use 9 microns, or 9,000 nanometers, is my beam diameter at the beam waste. So let's come up here. This is in millimeters, so that would be 0.009. All right, what do I put as divergence? We're going to leave that blank. We're going to come down here and use m squared. Since this is a single mode fiber and we're going to pretend that this is truly propagating a single mode, only the single mode Gaussian beam out of this, m squared would be, that's right, 1. We'll put 1 in there. And you'll notice that what happens is, yep, we get pretty much the same results. Let's put this at 1/4, okay? And let's take a look over here at the beam irradiance. You'll see the beam irradiances are the same for the fiber optic and what we're doing up here. So we've basically duplicated this information up here. Something else I might mention here, I'm just going to go up to the menu. I'm going to come over here. I'm going to look at miscellaneous functions, and I'm going to say I'd like to look at lens on laser and fiber optic calculations, and you'll notice this switches over here and it gives you the irradiance at range. Okay, this is the irradiance at range, and this is the major and minor diameter of the beam at range for the fiber optic stuff. So you can get lens on laser and fiber optic information over here. Just thought I'd point that out why we were setting here. Go back to miscellaneous functions. I'll set this back to correction factors and time limits, and that really is about all we want or need to talk about here. Not a lot else. We could look at this irradiance, but this is such a low irradiance that if you wanted to use something as a barrier, you could pretty much use anything you want here, from a piece of cardboard, paper, whatever, just so long as it's securely fastened so it doesn't move if you are using it as some type of barrier. Now, for this particular laser, you don't have much of an NOHD if we're dealing with the fiber. But if we're dealing with the collimated beam, well, that's a little different story, right? We have 22 meters. So if I've collimated this and I'm working sort of open beam with it for a bit, and I need to control this and make sure that 22 meters is probably a greater distance than the area that this thing is setting in, and I have other personnel and I want to just make sure everybody's safe, I'll put a barrier up. But the thing about it is this laser does not have the capability of igniting the material. You just need to make sure that at the wavelength 1550, whatever you put up there, it doesn't transmit any of the power through the material. Okay, I say that because sometimes we've run into situations where folks are using something like black polyethylene plastic, and they'll think that it's blocking the wavelength. But if you're in the near IR, guess what? It's not doing that good of a job. Near IR will pass through that. So you just want to make sure that whatever material you're using, it won't ignite, and it's truly blocking the wavelength. This is an easy laser to deal with. Okay, so I think that's about all we need to talk about here. Okay.